Hey everybody, welcome to this last video for part 3.4. What I'm going to do is talk about the common microscope and a refracting telescope. I thought I'd add this. This is sort of bonus material. I'm not going to ask you any test questions about the microscope or the refracting telescope, but since we've been talking about lenses and image formation with lenses, I thought I'd mention these. Since you guys have probably looked in a common microscope and maybe even a telescope. Okay, so these are examples of two-lens systems. So, oops, sorry, there we go. I'm sorry, my PowerPoint was hung up. Okay, so they're examples of two-lens systems. So they both use two positive lenses, two converging lenses. Now, if you've used a microscope before, you probably remember you look into one lens, that's called the eyepiece lens, and your specimen, if it's on a microscope slide, for instance, it's close to the other lens, which is known as the objective lens. And you may have even used a microscope where you have a choice of objective lenses. Like sometimes there'll be three lenses down there on a little circular stage that you can rotate and choose one of the lenses. And each of the lenses will have a different magnification. So we're going to do the ray trace for this two-lens system and see how the microscope actually magnifies the object. So here is an objective lens. It's just a single positive lens. I've put it on the optic axis. Now, the objective lenses, if you recall, they're very small lenses, small diameters, and that's because they have to have a really short focal length. So they have to have a lot of curvature. They have to be really rounded. So if they have to be really rounded, they can't have huge diameters, right? So that's why they're relatively small. So you can see I've put two focal points pretty close to this objective lens. Okay, so then what happens is the specimen or the object, it's going to be close to the objective lens. If you think back, if you've used a microscope, the slide is pretty close to the objective lens. But the object is outside the front focal point. So if you think about the geometry, if you have a single positive lens with the object close to the lens but outside the focal point, this is acting as a simple projector. So in fact, if you do the ray trace, here comes the ray trace, there is the real image formed by the objective lens of the microscope, and it's going to be formed somewhere in the tube in the body of the microscope between the objective lens and the eyepiece lens. So this is acting as a simple projector. Now, the eyepiece lens, you want it to act as a simple magnifier. So you can see I've put this positive lens here, and these two orange points represent the focal points of the eyepiece lens. And here's the neat thing about optical systems here. This image formed by the objective lens, you can now think of as the object for the eyepiece lens. So the eyepiece is just going to image the image formed by the objective lens. So when you go to do the ray trace for the eyepiece lens, you can now forget about these rays and just say, okay, I have an object here and I need to trace rays from this new object using my rules of ray tracing for this lens. So if we did that, we would draw a ray that is parallel to the optic axis, and that has to go through the back focal point of this positive eyepiece lens. And the other ray that we're going to draw is going to go right through the center of the eyepiece lens like that. So again, we're just thinking of this green arrow as the object arrow for the eyepiece. Now usually when we do ray tracing, right, our object is pointing up. But it's okay, this one just points down. We can still do the ray trace. Okay, now look at these two orange rays. You'll notice that they're diverging, right? They should, because the object is inside that front focal point. So what we do is we trace them backwards those dashed lines, and they appear to come from right there. So what the eyepiece is going to do is it's going to form a virtual image of this object, which is the image formed by the objective lens of the actual object, the specimen. So the microscope is a projector and a magnifier. So the objective lens acts as a projector, giving you a big real image that is then further magnified by the eyepiece, which forms a virtual image, and it's acting as a simple magnifier. So when you look into this, your eye's going to be over here, and you're going to see this image right here. Now, you can put some formulas on this. So, and again, you're not responsible for the formulas, but I thought it would be neat to label the different quantities, the distances and heights, and show you the formulas. So that right there, I labeled this as P sub O. This is the object distance for the objective lens. So that subscript O means objective lens. And then the image distance for the objective lens would be this Q sub O, from lens to its image. From that point right there to the eyepiece, that would be the object distance for the eyepiece, P sub E, because again, we're treating this as the object for the eyepiece. The image distance for the eyepiece is going to be from the center of the lens to its image, which is over here. That would be Q sub E, the image distance for the eyepiece. This right here would be the height of the object, H sub O. This would be the image height of the green arrow. That would be H O prime, the image height for the objective lens. But since that's the object for the eyepiece lens, that would be the object height for the eyepiece lens, H sub E. And then the image height for the eyepiece lens would be the length of this arrow right here. That would be HE prime. Okay? Oh, what I'm showing here is, we forgot about these rays right here when we went to figure out what the eyepiece lens does. But if you actually followed the refraction of those two rays that came from the objective lens, they would also diverge. I made them a light purple. They would also diverge. And if you trace them backwards, they also would appear to come from this common point right here. Okay, so that's just neat to finish off the tracing of those original rays. And then there's your eye. I mentioned that well, I hope that's not your eye, but anyway, your eye has to be over here catching some of this diverging light, and your visual system, right, will swear that that image is right here. Now, when you're looking in the eyepiece of a lens, right, you're not really aware that where the image is formed. You don't really think, oh yes, this image is formed behind the objective lens, right? No, you just see that image. But if you had to specify where exactly is the image formed, it's going to be back here, okay? Now, here are some formulas that you can use to design microscopes. So you might recognize this first one as the thin lens formula for the objective lens, and this is the magnification equation for the objective lens. Objective lenses will typically have magnifications of -40, -60, -80, up to about -100. The negative sign just means the image is inverted compared to the object for the objective lens. And usually people don't say minus when talking about the magnification of the objective. They'll just say 60x or 100x, okay, x meaning times. Okay, then for the eyepiece lens, you also see the thin lens formula. This is how you formulate the magnification, the so-called angular magnification for the eyepiece lens. If you recall when we were talking about the simple magnifier, I said in that case, you don't just look at the ratio of heights to define the magnification. You also have to be concerned about not only the height, but how far is the image formed from the lens. And when you do that, you can get a formula that's 25 centimeters over the object distance, P sub E, and that'll give you a good, useful magnification. Okay, again, don't worry about that. The total magnification of the microscope would be the product of those two. So typical eyepiece mags are 5x or 10x. So if you're using an 80x objective, officially minus 80, and a 10x eyepiece, and you're going to get a total magnification of minus 800 or 800x. Okay? And again, a simple optical microscope will have at most 100x objective and maybe a 10x eyepiece. So up to 1,000, but that's pushing it. Okay, and then, the distance between the lenses, you could also relate to Q naught and P sub E. That's what you see there. Okay. Oh, yes. And to get the most out of your eyepiece, because it's a simple magnifier, you would like to form this image about 25 centimeters from the eyepiece. Again, that 25 centimeters, that's the closest that you can have something to a healthy eye without it being blurry. Again, it's an approximate number. So you want to form the image as close to this lens as possible, but you still want to be able to see it clearly. So you'd like to get this around 25 centimeters from this lens. Okay, let's go on and talk about the telescope. Well, this is a refracting telescope. So this is one that uses a lens for the objective and a lens for the eyepiece. A lot of telescopes, more powerful telescopes, are what we call reflecting telescopes, which use a mirror for the objective and a lens for the eyepiece. But we're going to talk about a refracting telescope. So, for instance, one of the ones you see in pirate movies where they stretch out the tube and look into it, that's a two-lens or refracting telescope. So the telescope is neat. Again, it's a two-lens system. The objective lens is going to be a positive lens, and I marked the focal points right here. Now, what you want, though, is you want this to be a relatively long focal length, and you'll see why in just a minute. Okay, now, when you use a telescope, if you think about it, right, the objects are really far away. So they're so far away that in order for me to do an adequate ray trace, I can't really show you the object on the left here. Imagine that it's off the screen, far away from this objective lens. And imagine I'm doing the ray trace, and here are the two rays that are coming from the tip of the object arrow. See, this one's coming in parallel to the optic axis, so it goes through that back focal point. And this one's coming from the tip of the object arrow straight through the center of the lens. But again, the object is off the screen to the left. So look, these converge and they form an image right there. That intersection point, that's the tip of the image arrow. Oh my gosh, look at that little, you get a tiny little image right there. It is real. And if you think about it, this is acting as a camera, a simple camera, because the object is really far away from the positive lens. So you're going to get a tiny inverted image, real image, formed close to the lens, just outside the focal point. And at first glance, you might say, well, that's not good because we want the telescope to make far away things look bigger, right? And this lens is actually making an image that's even smaller than the object. And that's true, but here's the key. What it's doing is it's forming an image close to the lens. And because what we're going to do then is we're going to take the eyepiece lens and use it as a magnifying glass. So the eyepiece lens is acting just like it was for the microscope. It's acting as a simple magnifier. So what we want the eyepiece lens to do is to take this tiny real image and just magnify it. So the role of the objective lens is to form a real image so close to the eyepiece lens so that it can then magnify it. So if you continue with the ray trace, right, for a magnifier, you'll get that. Those two rays are diverging, trace them back. There's your eye catching the diverging rays, and you'll see a virtual image right there. Now, if I were to measure, if I could, because this is a virtual image, so I can't put a ruler on it, because if I put a ruler there, a paper there, I'm not going to see that. But that height is much, much, much smaller than the actual height of the object. Like if you're looking at the moon, for instance, the actual diameter of the moon is humongous compared to the diameter of this virtual image. However, because this virtual image is formed close to your eye, you'll see the moon to be bigger. Again, when using a magnifier, it's not just about the height. It's also about the distance. So again, because that image is formed close to your eye, you'll see the moon image as being much bigger than if you just looked at the moon without the telescope. Okay, now you can get some formulas involved. It turns out, I'll go through this quickly. It turns out that the object image distance, I should say the objective image distance, is close to the focal length of the objective. You see how that little green arrow is formed almost at the green focal point? And similarly, the object distance for the eyepiece is approximately the focal length of the eyepiece. So the distance from that little green arrow to the lens is approximately the distance from that orange focal point to the lens. If you make those approximations, you can do some triangle work, and you can actually, it's actually some trig work, but you can actually get an approximate expression for the total magnification of the telescope. And approximately, it's the ratio of the focal length of the objective lens to the focal length of the eyepiece lens. Officially, it's negative because the final image is upside down or inverted compared to the original object. So for a refracting telescope, you will get a total magnification that is approximately the focal length of the objective divided by the focal length of the eyepiece. Okay, that's why you want a long focal length lens for your telescope. Okay, all right. That's it. I thought, again, I'd just go over the microscope and the telescope since we've been talking about lenses. But again, I'm not going to ask you questions about them on the test, but they're fun to look at. Okay, I'll see you in the next part, part 3.5, where we're going to look at the eye and some things related to vision. Bye.